Hildreth, voy a leer un poco la bio, un poco general. Es diseñadora y dietista, ya principalmente trabajando en muchas cosas de comportamientos de alimentación, liderando distintos proyectos para IDEO, USDA, incluso con la ciudad de Austin, porque ella es de Texas. Y actualmente lidera el proyecto de Food Computers en el MIT Media Lab, en OpenAC, donde están haciendo, bueno, y obviamente van a contar mucho más al respecto, pero cómo transportar y hacer distintas recetas de climas que se pueden ir adaptando. En el caso de Arielle es doctora en química de la UC Davis. Trabajó mucho tiempo como la Head Research en NOMA y en MAD, donde obviamente se involucró muchísimo con la gastronomía. Y actualmente es la parte del sabor, voy a decir, de química en todo lo que es el desarrollo de los food computers, y específicamente ahora de lo que se va a hablar es un food computer para fermentar. Por favor, un aplauso para Hildreth y Arielle.
Hi, everybody. I mentioned before I'm Hildreth and I'm the Assistant Director for the Open Ag Initiative, and Arielle and I are going to talk a little bit about the future of farming and the future of agriculture. One of the things I want to sort of bring us back to from the original panel is that we think that the future of food or the future gastronomy systems actually have to look backwards in the food supply chain to the very beginning, to where food comes from, to the agricultural systems that we all rely on. So interestingly, and Linda brought this up, we think that that's also a very multidisciplinary place. Farming is traditionally, as many people know, farming is a really intense, hard thing to do, and it takes a lot of specialized knowledge. And what's interesting is that we think that the farm of the future is actually going to require many, many more people to be involved. And as Arielle said in the panel, also there's a difference between trying to go from a top-down approach, and we like to think that the farm of the future is very open, that it's open source, that it allows anybody to participate. And one of the things that the Open Agriculture Initiative does at the MIT lab is try to make farming accessible and easy, and much more, let's say, emotionally resonant for more people, so that more people come to farming. Thank you, that's perfect. Come to farming as a natural profession, which is probably not the first thing we think of. So the way that I describe it, I'm going to talk over here just to balance things out. Okay, I'll also take that. So when we're talking about open, we're talking about accessibility, mostly. And I'm just going to give you some context about what we do, what we build, because we build these weird things called food computers, which makes no sense, but you'll see what I mean. And if you could turn up the volume, or pump up the volume, as the kids would say. And if it doesn't come on, then I'm just going to keep talking so we can keep going. We work, yes, songs. The reason why I bring this video to your attention, this is sort of context overall, right? But when we're talking about the future of gastronomy and we're talking about preparing food and consuming food, which is really my bailiwick, my domain. I've come from the world of dietetics and nutrition. I've been trying to change how people make food choices for the last 15 years. I don't know if anybody, are there any other dietitians or nutritionists in the room? I don't know if you guys know, but that's also really hard to try and get people to change their behavior with regards to food. But I put this quote up here because eating is actually an agricultural act, and one of the things that Open Ag is trying to do is to get more people at the front side of the food supply chain so that we can start to talk about where food comes from, not only an awareness and a sort of increased exposure, but also a connection to it. This is probably going to happen a lot, so apologies. But when we talk about food, at least in English, it's a really popular thing to talk about. It's an easy entree into the conversation about food system challenges, about issues like malnutrition, which includes over and undernutrition, the reduction of arable soil or land upon which we can farm, GMOs, or the moralization of food choices when we're talking about climate, and climate we'll get into a lot. These are all things that I'm sure you're well aware of, and I don't need to go into detail. Also, the consumer, the person at the consuming side of the food supply chain, is super aware of these problems as well, and they're demanding more transparency in their food. So that, again, brings us back to where food comes from. We're also talking about, in 35 years, the farm of 2050 needs to be able to feed 9 billion people, 75% of which are going to be living in urban centers, and predominantly in the nearly developed world, in China, Russia, India, Brazil, the BRICS countries. So we focus on climate specifically. So the areas you see here in blue and green, those are currently the breadbaskets of the world. These are the places that are producing a lot of food for the rest of us. But what's going to happen in 35 years is that we're going to see a radical decline in the amount of food being able to be produced in those regions. So the typical breadbaskets of the world being a little bit of Brazil, largely the middle western part of the United States. These places just aren't going to be able to produce enough using the conventional agriculture methods that we have at hand. And we're talking about the potential militarization of food as well. These are the import-export relationships in our food supply system right now, places where food comes from and getting to. This takes a lot of resources. This makes demands of our planet and of our resources here, which are finite, that we're just not going to be able to sustain anymore. So what happens if instead of shipping food around, we ship data around? And so this brings us to this idea of climate. Is there a way for us to code climate, to code the environment, place it inside of a controlled growth chamber, and then download a climate and allow plants to grow anywhere in the world, wherever they are? This is the conceit behind controlled environment agriculture. So what we'd like to do is, instead of shipping food around the world, we ship data around the world. And that data creates environments in controlled growth chambers, and then you can produce food. I'm going to skip this. So these are what we call food computers. And it's the same thing as what we've grown to know as laptops or computers, right? It's a series of inputs. In this case, it's environmental variables like the pH of the soil, or in this case, the pH of water. We're talking about ambient temperature, root zone temperature. You can increase a series of inputs, run them through an operating system inside this controlled environment, and then you get a series of outputs, and you correlate the two. So for example, what happens if you run an environment, grow plants in this controlled, very controlled environment that's being sensed as the plants are growing and the climate is being maintained inside the box? What happens if you could increase the nutrient density of the plants or the yield of the plants? So for example, a reduction in the pH of the water is something that could increase the lycopene content of tomatoes or the vitamin C content of tomatoes. Often the nutrient density of plants is highly correlated to its flavor, which is something Arielle is going to talk a lot about. But this is the possibility, this is the potential. So when we say food computer, really what we're talking about is correlating a series of inputs, processing them. The plant is a really slow robot, basically. The world's slowest robot begins to process these inputs, and that's a climate recipe that goes inside, hangs out, plant processes it, and then the output is exactly what you want. So the output could be flavor, nutrient density, the yield. These are what we're researching right now using food computers. We use open source technology to do so, and this goes back to making sure that the farm of the future of 2050 is something that more people can get into. We use Arduino and Raspberry Pi microcontrollers. Most of the sensors and actuators that are inside a food computer are things that you can buy on Amazon. For example, if you need to cool the root zone of a plant that's growing in water, you need to have a cooler to do so. You need to be able to pump water through. We use a lot of the same stuff that fish tanks use. So we're trying to make sure that we have an interface that people can access their plants through, and this is something that we're working on right now to make even more engaging. But essentially what you're seeing here is a series of recipes. So if you want to grow bok choy, or if you want to grow radishes, or if you want to grow corn, or if you want to grow cotton, there's a recipe for that that will optimize exactly what you want from that corn, or exactly what you want from that basil, for example. Farming is not a very popular word or profession, at least in the United States, and that's not just in the United States. And so one of our missions and visions is trying to create 1 billion new farmers for the world by 2050. Small things, small goals, really, at the Open Agriculture Initiative. The reason why I say it's not just in the United States, we're looking at less than 2% of Americans employed by the agriculture sector. This extends also to the developing world, and it's mostly because folks are moving away. See, this is my marker for you. Folks are moving away from farming and moving away from rural areas into those urban centers. So we're losing knowledge. The average age of farmers is over the age of 58, at least in the US. And this is in Japan, this is Africa, this is in Brazil, this is in the United States. So how do we get farmers from looking like this to looking like this? We're in the 4th agricultural revolution at this point, and we need to be thinking about farming a little bit differently and trying to ask people to think about themselves as farmers. This is another farmer. How can we do this? How can we give ourselves a green thumb in the digital age? We are all farmers. I'm telling you, I'm the last person that would ever have thought of herself as a farmer, but that's how I identify myself now. These are farmers, more farmers. I mentioned that we work a lot with kids. This is a ripe age for the idea of planting farming as a new profession, and if you want anybody to tinker with open source technology, kids are the best to do it. This is a farm. These are farmers. This is a farm. We have a community that's rapidly growing. In 2016, this was our community. Right now, we've got about 33 countries. At some point, somebody's in a build of a personal food computer. They're able to do so, and they're using the open source code that's available on our GitHub. They're using our wiki and all of the build materials in order to make these things themselves. And these are just people who decided they wanted to build a food computer. We don't pay them, I promise you. But in order to be a new farm, right, you need new tools. And so Arielle's going to talk a little bit about what we're using as far as tools to get us to optimize plants, right? To optimize whatever we want. We're using computer vision, depth image sensing. This is basically a 3D camera. This is a Microsoft Kinect that's helping us figure out how to optimize for plant biomass, right? Because we are going to have to feed 9 billion people. So this is small, right, personal food computers, but we're also talking about the shipping container size and even larger. How do we determine that these climate recipes are working, and how much can we get from the plants that we're growing? That's a mess. This is a farmer of the future. So we're also working with NASA. In fact, our team is headed out to NASA and the Kennedy Space Center in July to try and figure out how to get these farmers of the future to be able to use food computers on other planets, let's say. So in order to get more folks thinking about farming and to bring the focus of the food system challenges and sort of future gastronomy systems back to the beginning of the food supply chain, we're talking about lots of farmers. And the thing about farming, like I said, is that it's hard. It's actually changing a behavior at the beginning of the food supply chain as opposed to just changing folks' behavior at the end of this food supply chain, which is, it's definitely an art. This is a concept that was built by Neri Oxman, who leads the mediated matter at the MIT Media Lab. She's a computational scientist and an architect, but one of her sort of great passions and I think gifts is that she's able to really get us to think about science and engineering and art and design all together. And you'll notice here that art and design are the sort of domain of changing behavior. And it's design and art that helps us reshape how we perceive the world, right? So we're talking about basically preparing for the new world, the new food system, and art and design really help us with this. So when we're talking about changing behaviors at the beginning, this is science, this isn't sexy. Not a lot of people know what Bayesian optimization with Gaussian process regression is, except for maybe Matthew and Arielle in the room. But artists and designers help us think about, well, what if? What if we could take the microbiome of the root and we manipulate one strain of bacteria and that changes the color of the plant? That's something that would get people sort of emotionally involved in growing a plant for the first time, for example. What if when you're working with the interface of a food computer, it's actually talking with you in Italian because it's growing Genovese basil? Or if it's growing Thai basil, it's going to speak to you in Thai, right? That's nasty. What happens if, and we do grow cotton as well in food computers, you change the color or the strength of the strands of cotton and you can grow your own genes. So these are ways to sort of personalize and get folks thinking about farming in new and interesting ways, more creative ways. We are working on growing our community, getting into more schools. We're adding Scratch. Scratch is a coding language for kids. But this is all a way of essentially bringing the idea of farming to more people, to making it more accessible. Because we all can be farmers, we just need to sort of identify ourselves as such. And now Arielle's going to talk a little bit about all the different kinds of farmers we can be.
Yeah, so I think there's probably not going to be any one farm of 2050, but what we can do is try to enable the farmer of 2050. But if you look back 100 years to the farmer of 1950, this is like the dawn of the Green Revolution. This is a farmer focused on scale, intensification, breeding new varieties for yield, and general flattening and centralization. So, we have 33 years to build new tools for the farmer of 2050. And so what kind of farmer will that be? Well, why don't we build tools for the farmer of flavor? And I'm going to take you kind of under the hood about how we're doing that at OpenAg right now. So what is flavor anyway? I had about half an hour's worth of slides, but I cut it down. Flavor is the combined sense of taste and smell, and both of those come from molecules. So if we're talking about flavor, we need to look into molecules. So some flavor molecules come from purely chemical processes. So this very large molecule on the left is called lignin. It's the primary structural component of wood. And when you burn it, it breaks down into much smaller molecules that have the smoky and spicy flavors and smells that you associate with smoke. So the smell of smoke literally comes from the breakdown of wood through fire. There's also a lot of molecules that are produced through biosynthesis. So this is just a selection of maybe there's at least like 1 million to 10 million different flavor compounds produced in nature. These are some. They smell like grass. They smell like herbs. They smell like tarragon. They smell like pine. They smell like wasabi. A huge amount of chemical and sensory diversity. So the reason that all of this complex chemistry comes into existence through biology is because of ecological interactions which are largely mediated and transacted through molecules. So the way that a plant responds to climate, that a plant responds to insects, that soil microbes respond to animals and vice versa is largely played out through different molecules that we happen to be able to perceive as flavors. So the physical and chemical characteristics of an organism are called its phenotype. This is to contrast with the genotype, which is its particular set of coded genetics. So if we're just like us, humans, plants, mice, molds,
What you're given and then
anything that's alive. So if we want to be altering physical and chemical characteristics, the phenotype, we can either alter the genetics, breed new things, do GMO, or we can alter the environment, so try to mediate some of these ecological interactions to make new or more or better flavor molecules. This is one of the experiments that we're doing now. I'm going to try to walk you through it. So we start out with the way that this sort of environment, genotype, phenotype loop works is you start out with, in this case, a basil plant that has a particular phenotype with like a little bit of flavor molecules. Then you add some stress, ecological interactions in a climate recipe. A particular gene gets activated, translates into enzymes. The enzymes act in a cascade of various primary molecules like amino acids, creates specialized molecules like this linalool or that cineol. So the end result is that you have the same organism, but with many more and a larger amount of these spicy herbal flavor molecules. What this means practically, if you have a system where you can control the environment, is that these ecological interactions and stressors become new control loops for controlling phenotype. So we're not just limited to planting one plant, and that's the result that we get. We can change its amount of water, the UV exposure, the amount of heat that it's exposed to. If there's some insect predators, we can introduce those. pathogenic fungi.
Basically build torture boxes.
Yeah,
for
I mean,
plants.
really the goal is to hit on exactly the optimum peak of stress so that the plant produces everything that we want, but that it's not so stressed that it rebels and refuses to thrive. So yeah, all of these are now new control loops for us. So the current experiment that we're working on, we stress out basil by applying extremely hefty doses of ultraviolet light on them.
We give it a sunburn.
Yeah. And it produces double and triple and up to 9 times as much of these natural basil flavors coming from molecules like ocimene, which is green and woody, eugenol, which tastes like cloves, linalool, which is herbal and floral, and some of these other ones. So we literally grow the basil. There's some ultraviolet lights above it. Harvest it. I analyze it using GCMS, and then we put the data out into the ether and either do a multivariate regression ourselves, or we have, oh no. You can read all my texts too. But
Look for the good stuff.
yeah. If anyone wants to text me a photo right now, it'll show up for everybody.
It's new participatory PowerPoint presentation.
The end result is that we have like several iterations. We analyze the data. Since all the data is totally open, anyone who is able to analyze data and wants to give it a stab can do that. So we've had some artificial intelligence and machine learning groups do that. To the point where on our 3rd and 4th iterations of basil, we've increased the volatile output by, in some cases, 1,000%, so 10 times as high. So it's like...
Which we wouldn't have known otherwise.
No, I mean, so we can like make a guess from the last experiment, but we're really optimizing with this machine learning thing. Yeah, Funk engine.
Which is part of so when we're stressing the plants out, we're continuing to collect its data, right? So it's telling us, it's sending the signals that it's stressed out, and we're collecting that, and we're trying to maintain the environment in which we're stressing it out. But the thing is that we're also now trying to run that data through algorithms as the plant is growing, right? So we're essentially going to end up being able to tweak the climate recipe during the growth cycle of the plant so that we continue to optimize for, in this case for basil, the expression of certain volatile
molecules.
That's what happens when you fly from the United States. Yeah. Volatile compounds. So this is an application of artificial intelligence and machine learning on top of the data as it's being collected, which then actuates and actually changes the environment as the plant is growing. So,
well, and when you're
real-time manipulation.
when you're creating these stressful environments for plants, it's not just flavor molecules that they're producing more of. They're producing more compounds that have antioxidant properties, antifungal, antimicrobial, and other various bioactivities in
They're
humans.
tasty and they're healthy and they're stressed out.
It's the perfect combination.
Yeah.
So yeah, we've got some basil. This is like what Hildreth showed in the video. We have our very large multi-shipping container set up right now. So we're going to start producing about 50 pounds of basil a week.
That's it, man.
Yeah, that's.
So you guys don't get to see.
I've given up.
Cool. So.
But I've also. So the farmer of 2050 will be growing plants in farms, but the farmer of 2050, in the interest of extending as many techniques as possible to make delicious food, will also be farming microbes and doing fermentation. So I've brought our latest prototype here. We call it the Fermentabot. So it's a fork of the food computer setup that, we're good. Okay, that is able to control the environment that microbes are growing in.
And this is what we mean by being an open source model, right? So we want more people to have access to this technology so that they can build their own food computer, regardless of what that ends up being. In this case, building a fork of or a modification of a food computer so that it ferments food. It's one way you can modify a food computer.
So yeah, just as with plants, the interactions between microbes, molds, bacteria, fungi, things like that, and their environment, the food that they grow on, is mediated very much by chemistry, and a lot of these molecules are very tasty. Yeah, so fermentation is literally creating flavors on a molecular level using microbes as tiny machines for transformation. And these are just some of the many delicious molecules that you can make. One of the most delightful fermentations is called koji. It's a mold called Aspergillus oryzae that's native to East Asia that you grow in grains and then can have a cascade of sake, miso, soy sauce, amazake, and other delicious things. So we're actually growing some koji right now in here, and I'm just gonna quickly walk you through koji and other fermentations. The success is very much based on environmental control, so exactly what we do at OpenAg. So some of these very traditional methods that you can see, weighting vegetables or putting mats over it. Well, one of them is controlling water content, keeping oxygen out. Other things are controlling temperature and humidity. Other things are including oxygen. So these are very low-tech, analog ways of actuating an environment. Some of the early experiments before we even came to MIT, we did at NOMA, was actuating temperature and humidity using shipping containers and a much smaller brain than we have now. These are prototypes of or a proof of concept of the very first fermentabots where we're using commercial controllers to actuate temperature and humidity. And this is the Fermentabot 1.0, the one that came just before this one, where we can actuate temperature and humidity, which can control about 1,000 different microbial species, and sensing oxygen, carbon dioxide, pH, and the electrical conductivity, the ion composition of the fermentation. So if we have that website that I gave you the link for, we can actually access the user interface to this in real time. This is hooked up through the internet directly to this little guy. You could read on here the air temperature, humidity, and CO2. You can set temperature and humidity with buttons. But here you can see that there was a giant mystery drop in temperature earlier this afternoon, and that the oxygen level of the air has gone significantly up. So I can access this from here. I'm leaving this Fermentabot here for Diego to play with and generate some more data, and we can share these interfaces with each other and check in on each other's fermentations. So that's very exciting. I'm very excited about that.
I'm really excited.
Yeah, and if any of you would like your own Fermentabot, all of the designs for hardware, software are open source and on our GitHub.
You don't even have to tell us what you do with it, really.
You don't have to share this with us.
No, you don't.
Just let us know if you make one.
Yeah.
Yeah, that's all. I mean,
Well, so
good for me.
we just wanted to give you guys another sort of idea about what agriculture can mean or what gastronomy can mean sort of at the beginning of where we get our food, right? And what sorts of technologies we're talking about that can be either fairly low tech or really high tech, and that all the solutions sort of are in that beautiful middle ground of low tech and high tech. We are not mutually exclusive, for example, with conventional agriculture. I think that's really important to admit. We're working a lot with companies who have lots of data from in-field, because we are trying to create an open source data common for anyone to be able to download the climate recipes, and it will take more than just our knowledge at OpenAg at the Media Lab. We recognize that part of changing the future of food or getting us to the food system of 2050 in a healthy and sustainable way is sort of being humble about the food system and recognizing that it's going to take so many more experts than we could possibly supply. And that's why we want to make this as open and accessible as possible in a sort of citizen science farm, right? So the farm is global. But we hope that you guys will participate. Our website is openag.mit.edu, and from there you can find all of our little digital channels, including being able to get to the code, downloading the bill of materials, and even the data that we are generating. And yeah, and stay tuned. Thank you.
Thank you.